And now in this lecture we'll answer two questions. In the first question we'll find out the area of this green shape, and in the second question we'll find out the length of line segment PQ is equals to x. We have to find out the value of x. So we start with the first question. In the moment we have a circle inside this big semicircle. We know that this is line segment AQ that is equals to 4 units in its length. This is angle PQA, that is a right angle. This is line segment TB that is equals to 1 unit in its length. This is angle STB, that is a right angle. Again, our task is to find out the area of this green shape. So first of all, we will define the radius of the big semicircle as x. And the radius of this circle is y. AB is the diameter of the semicircle. The radius of this semicircle is x, therefore the diameter AB must be equal to 2x. We'll define the center of this small circle as O, and we'll define the center of this big semicircle, this point, as point C. We'll define the point of tendency of tangent AB with this small circle, this point is point M. We'll define the point of tendency tangent ST with this small circle, this point is point L. We'll define the point of tendency of tangent PQ with this small circle, this point is point H. And finally, we'll define the touching point of the circle with the big semicircle. This point is point K. In the next step, we join points O and N together by straight lines. Point O is the center of this small circle, point N is the point on the circle itself. Therefore, ON is the radius of this circle that is equals to y according to our definition. The radius ON that equals to y, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. This gives us the question that this is angle PQA, that is a right angle. AB is a diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to the rule that states, rule 3, that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point Q? we have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points O and H together by a straight line. O wedge is of course the radius of this small circle, therefore it is equal to y according to our definition. The radius O wedge that is equal to y, the radius O wedge is drawn to point H, that is the point of tendency of tangent PQ with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius AO. If PQ is perpendicular to AO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum rule, rule 1. So inside the quadrilateral edge O and Q, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule. Then the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral edge O and Q, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle in front of square. So related to this quadrilateral edge O and Q is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle edge O and Q, side edge O must be equal to the opposite side QN. But edge O is y, therefore the opposite side QN must be also equal to y units in its length. In the next step, we join points O and L together by a straight line. OL is of course the radius of this small circle, is equals to y. The radius OL that is equals to y, the radius OL is equal to point L, that is the point of tendency of tangent ST with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the sum rule, rule 1. So inside quadrilateral OLTN, we have 1, 2, actually, what is the size of this angle? We know that angle STB is equal to 90 degrees in its side according to what is given us in the question. AB is a diameter, it is a straight line, so if you focus on the upper side of the straight line AB at point T, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of the straight line AB at point T, we have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So inside quadrilateral OLTN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OLTN, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle in front of square. So we relate to quadrilateral OLTN as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle OLTN, side OL must be equal to the opposite side TN. but OL is y, therefore the opposite side Tn, must be also equal to 1 unit in its length. This is line segment QT. Line segment QT is a straight line because it is part of this big straight line AB. AB is the diameter is a straight line, and therefore part of the straight line AB, QT, must be also a straight line because a part of the straight line must be a straight line. So QT is a straight line, and therefore the length of the straight line QT will be equal to y plus y, that is 2y. So QT equals to 2y units in its length. Another way to find out that QT is a straight line, we can see that angle QNT is equal to 90 degrees plus 90 degrees, that is 180 degrees. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, QT is a straight line. So, therefore, QT equals to y plus y, that is 2y. So, what is the length of AB? AB equals to 2x. It is the diameter of the semicircle that is equals to 2x. AB equals to 2x, and AB equals to AQ. Again, AB equals to AQ plus QT. Plus TB. Repeat again. AB in total equals to AQ plus QT plus TB. So AB is equals to 2x is equals to AQ is 4, according to what is given as the question, plus QT. QT equals to 2y units in its length, plus TB. TB equals to 1 unit in its length, according to what is given as the question. So in total, we found out that 2x equals to y plus 2x equals to 4 plus 2y plus 1. So 2x in total equals to 2y, and 4 plus 1 is 5. So 2x in total equals to 2y plus 5. Here we will subtract 2y from this equation, and we get that 2x minus 2y equals to 5. Here we take a root out of this, here we take out 2 as a common factor from those two expressions. So inside the brackets we left with x minus y equals to 5. So here we will divide this equation by 2. And finally we get that x minus y equals to 5 over 2. 5 over 2 is 2.5. So total we found out that x minus y equals to 2.5. What is the length of this line segment Cn? From the drawing it is very easy to see that Cn equals to Cb minus Nt minus Tb. Okay, again, Cn in total equals to Cb minus Nt minus Tb. Okay, again, this short line segment Cn equals to Cb minus Nt minus Tb. So Cn in total equals to Cb. Cb is the radius of this semicircle. That is equals to x according to our definition. Minus Nt. Nt equals to y. Minus Tb. Tb equals to 1 according to what is given in the question. So in total we actually found out that Cn equals to x minus y minus 1. So Cn equals to x minus y. But x minus y is 2.5. So I can substitute x minus y by 2.5 minus 1. 2.5 minus 1 is 1.5. So in total we found out that the length of the short line segment Cn is equals to 1.5. Cn equals to 1.5 units in its length. So this is the short line segment Cn is equals to 1.5 units in its length. In the drawing we have an internal notch between the small circle and the big semicircle. That is to say, they touch each other internally at this point K. Point K is the touching point between the small semicircle and the big semicircle. And whenever we have an internal notch between two circles or semicircles, we can implement rule 9. So I repeat quickly rule 9. According to rule 9, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. So in the moment we have, this is the big circle, the center of this big circle is here at point O. The center of this small circle is here at point M. The straight line that connects their centers together is of course the straight line OM. And according to this rule 9, the straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass through point P, that is their touching point. Or according to rule 9, OMP is one straight line. Again, OMP is one straight line according to rule 9. So we can implement rule 9 in our drawing. Why? Because in our drawing, we have internal notch between the small circle and the big semicircle, this point K. The center of the big semicircle is here at point C. The center of this small circle is here at point O. The straight line that connects their centers together is of course the straight line CO. And according to rule 9, the straight line CO must pass through point K, that is their touching point. Again, according to rule 9, the straight line CO must pass for their touching point, that is actually point K, or COK is one straight line. Again, according to rule 9, COK is one straight line. So we join point C and O together by straight line, and according to rule 9, the straight line CO must pass for the touching point, that is actually point K. So you can see from the drawing that the straight line CO indeed passes for the touching point, that is actually point K. Exactly according to rule 9. What is the length of this this line segment CO? Actually, CO equals to CK minus OK. It's very easy to see from the drawing that CO equals to CK minus OK. So CO in total equals to CK. What is the definition of line segment CK? Line segment CK starts from point C, that is the center of the semicircle, and ends at point K, that is a point of the semicircle itself. So this is exactly the definition of a radius. Therefore, CK is the radius of this semicircle. That is equals to x according to our definition, minus OK. OK is the radius of this small circle. That is equals to y, also according to our definition. So in total, we actually found out that CO equals to x minus y. This line segment CO equals to x minus y. But we have already found out that x minus y equals to 2.5. Therefore, CO equals to 2.5. We have already found out that Cn equals to 1.5. So in the next step, I'll copy the right triangle OCN, this right triangle OCN, in a new page, and we will implement on this right triangle OCN the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. We have found out that Cn equals to 1.5 units in its length. We just right now found out that the hypotenuse CO equals to 2.5 units in its length. And ON is the radius of this small circle. ON is the radius of this small circle, that equals to y. Here by PT is the relation for Pythagoras theorem. So actually this is the right triangle CON that I got from the original drawing. This right triangle CON, according to the Pythagoras theorem, OC squared, that is the square of the hypotenuse, equals to ON squared plus NC squared. So I write it down. OC squared, that is the square of the hypotenuse, equals to ON squared plus CN squared. The hypotenuse OC equals to 2.5 units in its length, and therefore OC squared is 2.5 squared, that is 6.25. And it is equals to ON squared. ON is y, therefore ON squared is y squared plus CN squared. CN equals to 1.5, therefore CN squared is 1.5 squared, that is 2.25. So in total, if you found out that 6.25 equals to y squared plus 2.25. Here we will subtract 2.25 from this equation, and we get that 6.25 minus 2.25 is 4, so 4 equals to y squared. Here we take the root out of this equation, and finally we get that y equals to the square root of 4, that is 2. So if you found out that the radius of the small circle y is equal to 2 units in its length. The radius y equals to 2 units in its length. We have already found out that x minus y equals to 2.5. But we just right now found out that y equals to 2. Therefore x minus y is x minus 2. That is equals to 2.5. X minus 2 equals to 2.5. Here we will add 2 to this equation, and we get that x equals to 2 plus 2.5 is 4.5. 4.5 is 9 over 2. So in total we found out that the radius of this big semicircle x is equals to either 4.5 or 9 over 2 units in its length. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing it is very easy to see that the area of the green shape is equal to the area of the semicircle minus the area of the circle. So again, the area of the green shape equals to the area of the semicircle minus the area of the circle. The area of the semicircle is equal to the area of the circle over 2. The area of the circle is pi x squared. So pi x squared over 2 is the area of this semicircle. Minus the area of the circle. The area of this small circle must be equal to pi times y squared. Pi times the radius squared, that is pi y squared. So in total, we found out that the area of the green shape equals to pi x squared over 2 minus pi y squared. So it is equals to pi over 2 times x squared. X is 9 over 2, therefore x squared is 9 over 2 squared. Minus pi y squared. Y is 2, therefore y squared is 2 squared, that is 4. So in total, we found out that the area of the green shape equals to pi over 2 times 9 over 2 squared minus 4 pi. We'll open the brackets of this expression and we get that this expression equals to pi over 2, and we have 9 squared over 2. 9 squared is 81 over 2 squared, that is 4. So in total, the value of this expression equals to 81 pi over 2 times 4, that is 8. So if we found out that the area of the semicircle is equal to 81 pi over 8 square units in its size, minus 4 pi, that is the area of the circle. Here we multiply minus 4 pi by 8 and then we divide it by 8 in order to account front of this expression, and we get that minus 4 pi times 8 is minus 32 pi divided by 8. So 81 pi minus 32 pi is 49 pi divided by 8. 49 pi over 8 is 19.24 square units. So the answer to the question is that the area of this green shape, it is equal to either 49 pi over 8 square units in its size, or in terms of numbers, the area of this green shape is equal to 19.24 square units in its size. So we finish with the first question. In the next step, I present to you the second question. We'll solve the second question of this lecture. In the second question, our task is to find out the length of this short line segment PQ that is equals to x. We have to find out the value of x. So in the drawing, we have a semicircle. This is point O, that is the center of this semicircle. this is line segment OS, that is equals to 2 units in its length. This is line segment SB, that is equals to 1 unit in its length. This is angle PTS, that is a right angle. This is angle PQS, that is also a right angle. Again, our task is to find out the length of this line segment PQ, that is equals to x. We have to find out the value of x. So first of all, we will complete the semicircle to a circle. And we will extend line segment TS until it touches the circle. We define the touching point of the extended line segment TS with the circle. This point is point M. In the next step, we join points P and M together by a straight line. So by joining points P and M together by straight line, we can do triangle PTM. This is triangle PTM, that is equals to 90 degrees in its size, according to what is given in the question. And triangle PTM subtend on chord PM. Okay, again, triangle PTM, that is a right angle, subtend on chord PM. So here we can implement rule 5. Okay, quickly rule 5. According to rule 5, any peripheral angle that is equals to 90 degrees must subtend on the diameter of the circle. We have a circle. This is peripheral angle MAN, that is a right angle. According to this rule 5, any peripheral angle that is equals to 90 degrees in its size must subtend on the diameter of the circle. Peripheral angle MAN is a right angle, and indeed it subtends on the diameter of the circle, that is MN, because MN is the diameter of the circle. So according to rule 5, any peripheral angle that is equals to 90 degrees in its size must subtend on the diameter of the circle. We can implement rule 5 in our drawing. Why? Because in our drawing, peripheral angle PTM is equal to 90 degrees in its size, and therefore it must subtend on the diameter of the circle. Peripheral angle PTM subtend on PM, and therefore according to rule 5, PM must be the diameter of the circle. So PM is the diameter of the circle according to rule 5. Point O is the center of this circle according to what is given in the question. Point P is the point of the circle itself, therefore OP is the radius of this circle. OB is also the radius of the circle. So OB in total equals to OS, that is 2, plus SB, that is 1. 2 plus 1 is 3. So the radius of this circle is equals to 3 units in its length. Therefore, the radius OP must be equal to 3 units in its length. OM is also the radius of this circle, and therefore it is equal to 3 units in its length. In the next step, we will do a construction. That is to say, from this point S, we will do perpendicular on the diameter PM. Again, from point S, we will do perpendicular on the diameter PM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and the diameter PM. This point is point N. By doing this construction, we're going to do the right triangle S and O. Those two angles, they are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. In the right triangle POQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this right triangle ONS, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that the upper right triangle PQO is similar to the lower right triangle SNO. I will explain anyway why those two right triangles are similar to each other. First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if we found out that all the figures of this upper right triangle PQO are corresponding equal to all the figures of this lower right triangle SNO. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. I should find out that the upper right triangle PQO is similar, this is the sign of similar, to the lower right triangle SNO according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the small right triangle SNO over side PQ of the upper right triangle PQO is equal to side SO of the right lower triangle SON over side PO of the upper right triangle PQO. Repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN of the lower right triangle SNO over side PQ of the upper right triangle PQO is equal to side SO of the lower right triangle SNO, or side PO of the upper right triangle PQO. SN is the missing side, so we leave it as it is. Over PQ. PQ is the line segment that we are looking for in this question, and it is equal to x. We have to find out the value of x. And it is equal to SO. SO equals to 2 units in its length, according to what is given as the question. Over PO. PO is the radius of this circle that is equal to 4 units in its length. So in total, we have found out that Sn over x equals to 2/3. Here we will multiply this equation by x, and finally we get that the missing side Sn is equal to 2/3 x. Sn equals to 2/3 x. So if you found out that this is the missing side Sn, that equals to 2/3 x. In the next step, we define the size of this angle as beta. So in this small right triangle SNM, this angle equals to beta. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we will focus on the big right triangle PTM. On the big right triangle PTM, this is angle beta. So actually, angle beta is a common angle that belongs to both triangles. Angle beta belongs to the small right triangle SNM. Angle beta also belongs to the big right triangle PTM. So in the right triangle PTM, this angle is beta. This angle equals to 90 degrees in its size, and therefore this third missing angle must be equal to 90 degrees minus beta, according to the symbol that I mentioned a couple of times, that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that the big right triangle PTM is similar to the small right triangle NSM, according to angle similarity rule. I will explain anyway why those two right triangles are similar to each other. Why the big right triangle PTM is similar to this small right triangle NSM. First of all, this is angle beta, that is a common angle that belongs to both triangles. So we can write down that angle beta equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta, and therefore they are equal to each other. So if you found out that all the figures of this big right triangle PTM corresponding equal to all the figures of this small right triangle NSM. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. If you found out that the big right triangle PTM is similar, this is the sign of similar, to the small right triangle NSM, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side Sn of this small right triangle NSM over side PT of the big right triangle PTM is equal to side SM of the small right triangle NSM over side PM of the big right triangle PTM. Been again from the fact that the big right triangle PTM is similar to this small right green triangle NSM, we will derive that the following relationship exists between their sides. We will derive that side SN of the small green right triangle NSM over side PT of the big right triangle PTM is equals to side SM of the small green right triangle NSM over side PM of the big right triangle PTM. We have already found out that NS equals to 2/3 x. NS is 2/3 x. Two-thirds x over PT. Actually, it is given us a question that side PT equals to side TM. Side PT equals to TS. Here, PT equals to TS. PT equals to TS according to what is given us the question. PT equals to TS. So if we define the length of side PT as A, then the length of side TS must be also equal to A because they are equal to each other according to what is given us the question. So PT is A according to our definition. And it is equals to SM. SM is the missing side. This is side SM. That is the missing side, so we leave it as it is. SM over PM. PM is the diameter of this circle. Therefore, it is equals to 2x. It is equals to PM is the diameter of the circle. The radius is 3, therefore the diameter must be equal to 6. So PM is the diameter of the circle, therefore it is equals to 6 units in its length. It is twice as long as the radius that is 3. So PM is the diameter of the circle, that is equals to 6 units in its length. So in total, if you found out the 2/3 x over A equals to SM over 6. Here we will cross multiply this equation and we get that two-thirds x times 6 equals to A SM. So according to equation 1, if you found out that two-thirds x times 6 equals to ASM. 6 over 3 is 2, and 2 times 2x is 4x. So in total, this expression equals to 4x. So 4x equals to ASM according to this equation, equation 1. Here we can implement rule 15. So I put quickly on rule 15 and we will implement rule 15 in our drawing. According to rule 15, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. So in the drawing we have a circle and we have, this is chord AB that intersects with chord AD at point O. Point O is the intersection point of chord AB with chord CD. According to this rule 15, in this drawing, the following question is true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule 15 in our drawing. Why? Because in our drawing, we have chord TM that intersects with chord AB at point S. Again, chord TM intersects with chord AB at point S. So write it down. If you found out that in our drawing, chord TB intersects with chord AB at point S. So actually, all the requirements of rule 15 are satisfied, and we can implement rule 15 in our drawing. According to rule 15, the following equation will be true. That TS times SM equals to AS times SB. Again, TS times SM equals to AS times SB. So I write it down. TS times SM equals to AS times SB. Repeat again, in our drawing, chord TB intersects with chord AB at point S, and therefore the following equation will be true, that TS times SM equals to AS times SB. TS equals to A according to our definition. Times SM. SM is this inside, so we leave it as it is. So in this side of the equation we have A times SM, and it is equals to AS. What is the length of AS? AS in total equals to AO plus OS. So AS in total equals to AO. AO is the radius of the circle that is free, plus OS. OS equals to 2 units in its length according to what is given in the question. So in total, AS equals to 3 plus 2, that is 5. So AS equals to 5 units in its length times SB. SB equals to 1 unit in its length according to what is given in the question. So in total, if we found out that A times SM equals to 5 times 1. 5 times 1 is 5. So in total, if we found out that according to equation 2, this is equation 2. According to equation 2, A times SM equals to 5. This is according to equation 2, while according to equation 1, this is equation 1. According to equation 1, we found out that A times SM equals to 4x. So, I wrote it down. According to equation 1, we have found out that A times SM is equal to 4x. So we have two different equations for A times SM, and therefore we get equation 3 that states that A times SM according to equation 1 must be equal to A times SM according to equation 2. So write it down. So equation 3 states that A times SM according to equation 1 must be equal to A times SM according to equation 2. A times Sm according to equation 1 is 4x, and it must be equal to A times Sm according to equation 2. A times Sm according to equation 2 is 5. So in total, according to equation 3, we found out that 4x equals to 5. Here we will divide this equation by 4 and finally get that x equals to 5 quarters. 5 over 4 is 1.25 units. So actually, this is line segment PQ, this equals to x. Line segment PQ is equals to x. It is equals to either 5 quarters units, or in terms of numbers, it is equals to 1.25 units in its length. If it again, we should find out that line segment PQ is equals to x. It is equals to either 5 quarters units in its length, or in terms of numbers, p cubed is equals to x is equal to 1.25 units in its length. And that is the answer to the second question. In the next step, I have summarized the lecture. We'll start with the first question, of course. Our task in the first question is to find out the area of this given shape. So in the drawing we have a semicircle. In the drawing we have a circle inside this big semicircle. We know that this is line segment AQ, that equals to 4 units in its length. This is line segment TB, that equals to 1 unit in its length. We have angle, this is angle STB, this is right angle, and angle AQP, this angle is also a right angle. Again, our task is to find out the area of this given shape. So first of all, we define the radius of this big semicircle as x, and the radius of this small circle as y. In addition, we define the radius of this semicircle and the center of this the center of this small circle. This point is point O. We define the center of this big semicircle. This point is point C. We define the point of tendency of tangent AB with this small circle. This point is point N. Likewise, we define the point of tendency of tangent PQ with this small circle. This point is point N. We define the point of tendency of tangent ST with this small circle, this point as point N. And finally, we define the touching point of this small circle with this big semicircle. This point is point K. In the next step, we join points O and N together by a straight line. Point O is the center of this small circle. Point N is the point of the circle itself. Therefore, ON is the radius of this circle. This equals to y according to our definition. The radius ON that is equals to y, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. This gives us the question that this is angle PQA, that is a right angle. AB is the diameter of the semicircle, therefore it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point Q. Here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of AB at point Q? We have this angle that is the right angle according to what is given as the question, plus this missing angle in total must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its side. We join points O and H together by straight line. OH is of course the radius of this small circle that equals to y according to our definition. The radius OH that is equals to y. The radius OH is drawn to point H, that is the point of tendency of tangent PQ with this small circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius HO. If PQ is perpendicular to HO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule, rule 1. So inside quadrilateral edge O and C, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth angle. In total, they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth angle must be equal to 90 degrees in its size. So inside quadrilateral edge O and Q we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be its right angle in front of the square. So we went to this quadrilateral edge O and Q is right angle because it has 4 right angles. But we also know that the opposite sides of right angle are equal to each other. So left angle edge O and Q, side edge O must be equal to the opposite side NQ. But edge O is y, therefore the opposite side NQ must be also equal to y units in its length. This is angle STB, this is the right angle. So AB is the diameter, it is a straight line. So if we focus on the upper side of the straight line AB at point T, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of AB at point T? We have this angle that is the right angle, plus this missing angle. In total, the sum of those angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points O and L together by straight line. OL is of course the radius of this small circle that is equals to y. The radius OL that is equals to y. The radius OL is drawn to point L, that is the point of tendency of tangent ST with this small circle. And whenever you have radius that is drawn to the point of tendency, then tangent ST will be perpendicular to the radius LO. If ST is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside quadrilateral OLTN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth angle must be equal to 90 degrees in its size. So inside quadrilateral OLTN, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle in front of a square. So we went to this quadrilateral OLTN as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle OLTN, side OL must be equal to the opposite side TN. But OL is y, therefore the opposite side TN must be also equal to y units in its length. So in total, we found out that QT equals to y plus y. But before that, QT is absolutely a straight line because of the fact that QT is part of the straight line AB. Again, QT is part of the straight line AB, therefore it must be also a straight line. So, because of the fact that QT is a straight line, QT equals to QN plus NT. That is to say, Qt equals to Qn, that is y, plus Nt, that is y. So Qt equals in total to 2y. Okay, so we know that AB is the diameter of this circle, therefore it equals to 2x. The radius is x, therefore the diameter must be equal to 2x. So AB equals to 2x from one side. Again, AB equals to 2x from one side, but from the other side, AB also equals to AQ plus QT plus TB. Again, AB in total equals to AQ plus QT plus TB. From the other side, AB also equals to AQ plus QT plus TB. So AB equals to AQ. AQ is 4, according to what is given in the question. We just right now found out that QT equals to 2 y units in its length, and TB equals to 1, according to what is given in the question. So in total, we actually found out that AB is equals to 2x equals to 4 plus 2y plus 1. Okay, so here 2x equals to 4 plus 1 is 5 plus 2y. So 2x equals to 2y plus 5. Here we subtracted 2y from this equation and found out that 2x minus 2y equals to 5. Here we took 2 out of, it's a common factor from those two expressions. So inside the brackets we left only with x minus y. So in total we found out that 2 times x minus y equals to 5. Here we divided this equation by 2 and finally found out that x minus y equals to 5 over 2. 5 over 2 is 2.5. So we found out that x minus y equals to 2.5 units in its length. What is the length of the missing line 7? Line 7 CN. What is the length of this missing line 7? Line 7 CN. From the drawing it is very easy to say that CN in total equals to CB minus NT minus TB. Again, CN in total equals to CB minus NT minus TB. Repeat again, CN in total equals to CB minus NT minus TB. So CN equals to CB. CB is the radius of the semicircle that is x minus NT. NT is y and TB is 1. Again, CN equals to CB that is x minus NT that is y minus TB that is 1. So in total, CN equals to x minus y minus 1. X minus y is 2.5. So substitute x minus y by 2.5 minus 1. So 2.5 minus 1 is 1.5. So in total, we found out that the length of the short line segment CN is equals to 1.5 units. This is the short line segment CN. This is equals to 1.5 units in its length. In our drawing, we have an internal notch between this small circle and this big semicircle. Whenever you have an internal notch between two circles or semicircles, you can implement rule 9. So if you click on rule 9, according to rule 9, any peripheral angle that according to rule 9, if two circles touch each other internally, then the side line that connects their centers together passes through their touching point. Again, if two circles touch each other internally, then the straight line that connects their centers together passes through their touching point. In the drawing, we have two circles. This is the big circle with the center O. This is the small circle with center M. The straight line that connects their centers together is of course the straight line OM. And according to this rule 9, the straight line OM must pass through their touching point, that is point P. Again, the straight line OM must pass through point P, that is their touching point. Or OMP is one straight line. Again, OMP is one straight line according to this rule 9. So we can implement rule 9 in our drawing. Because in our drawing, we have internal between this small circle and this big semicircle. That is to say, those two circles touch each other internally in this point K. The center of this big semicircle is at point C. The center of this small circle is at point O. The straight line that connects the circles together is of course the straight line CO. And according to rule 9, the straight line CO must pass through point K, that is their touching point. Again, the straight line CO must pass through their touching point, that is point K. Or COK is one straight line. Again, COK is one straight line according to rule 9. So if COK is one straight line, it means that CO in total equals to CK minus AK. Again, CO equals to CK minus OK. CO equals to CK minus OK. So CO equals to CK. CK is the radius of the semicircle that is X. Minus OK. OK is the radius of the small circle, that is y. So total CO equals to x minus y. CO equals to x minus y. But we already found out that x minus y equals to 2.5. Therefore, CO that is equals to x minus y is equals to 2.5 units in its length. And we have already found out that Cn equals to 1.5 units in its length. In the next step, I go bit right target CON in a new page and we implemented the Pythagoras theorem on this right target CON. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle CON that according to the original drawing. In this right triangle CON, according to the Pythagoras theorem, OC squared, that is the square of the hypotenuse, equals to ON squared plus NOC. And OC squared equals to ON squared plus NC squared. OC is 2.5, therefore OC squared is 2.5 squared, that is 6.25. And it is equals to ON squared. ON is y, therefore ON squared is y squared plus Cn squared. Cn is 1.5, therefore Cn squared is 1.5 squared, that is 2.25. So in total, we found out that 6.25 equals to y squared plus 2.25. Here we subtracted 2.25 from this equation, and we found out that 6.25 minus 2.25 is 4, so 4 equals to y squared. Here we took out of this equation, and we found out that y equals to the square root of 4, that is 2. So if you found out that the radius of this small circle y is equal to 2 units. We have already found out that x minus y equals to 2.5. Y is 2. So x minus y is x minus 2, that is 2.5. X minus 2 equals to 2.5. Here we added 2 to this equation and found out that x equals to 2 plus 2.5, that is 4.5. 4.5 is 9 over 2. So actually found out that the radius of the big semicircle x equals to either 4.5 units in itself or 9 over 2 units in itself. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawings it's very easy to see that the green shape in total equals to the area of the semicircle minus the area of this small circle. But again, the area of the green shape is equals to the area of the big semicircle minus the area of the small circle. What is the area of the semicircle? The area of the semicircle must be equal to the area of the circle over 2. That is to say, it is pi x squared over 2, because x is the radius. So the area of the semicircle equals to pi x squared over 2, minus the area of this small circle. The radius of this small circle is y, therefore the area of this circle must be equal to pi y squared. So in total, if you found out that the area of the green shape equals to pi x squared over 2, that is the area of the semicircle, minus the area of the circle, that is pi y squared. X is 9 over 2, therefore x squared is 9 over 2 squared. So in total, this expression equals to pi over 2 times x squared, that is 9 over 2 squared, minus pi y squared. Y is 2, so y squared is 2 squared, that is 4. So in total, this expression equals to 4 pi. So here we open the brackets of this expression, and we found that pi over 2 times 9 over 2 squared. 9 over 2 squared equals to 9 squared, that is 81, over 2 squared, that is 4. So in total, the value of this expression is equals to 81 pi over 2 times 4. So it is 81 pi, and 2 times 4 is 8. So 81 pi over 8. And we have also minus 4 pi. So here we multiplied 4 pi by 8, and then we divided by 8 in order to become factor of this expression. So minus 4 pi times 8 is minus 32 pi divided by 8. 81 pi minus 32 pi is 49 pi, so it is 49 pi over 8. So if you found out that the area of this green shape, it is equal to either 49 pi over 8 square units in its size, or in terms of numbers, the area of this green shape equals to 19.24 square units in its size. So we finish with the first question. In the next step, I present to you the second question, and we answer on the second question of this lecture. Our task in the second question is to find out the length of this short line segment PQ is equal to x. We have to find out the value of x. So in the drawing we have a semicircle. Point O is the center of this semicircle. We know that this is line segment OS, that is equal to 2 units in its length. This is line segment SB, that is equal to 1 unit in its length. We also know that this is angle PTS, that is the right angle. And we also know that this is angle PQS, that is also a right angle. Again, our task is to find out the length of this short line segment PQ, that is equal to x. We have to find out the value of x. So in the first step, we completed the semicircle to a circle, and we extended line segment TS by a straight line until it touches the circle. We define the touching point of the extended line segment TS with this circle. This point is point M. In the next step, we join points P and M together by a straight line. By doing all those constructions, we're going to do peripheral PTM. This is peripheral PTM, that is equal to 90 degrees in its size according to what is given in the question. And peripheral PTM subtend on chord PM. Again, peripheral PTM subtend on chord PM. According to rule 5, any peripheral that is equal to 90 degrees in its size must subtend on the diameter of the circle. So peripheral PTM is equal to 90 degrees in its size, and therefore it must subtend on the diameter of the circle. Peripheral PTM subtend on chord PM, and therefore PM must be the diameter of the circle according to rule 5. Again, peripheral PTM subtend on chord PM. It is a right angle, and therefore PM must be the diameter of the circle according to rule 5. So point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle. OB is also the radius of the circle. OB in total equals to OS plus SB. So in total OB equals to OS, that is 2, plus SB, that is 1. So in total OB equals to 2 plus 1, that is 3. That is to say the radius of this circle is 3. So OP is the radius of this circle, that is 3. OM is also the radius of this circle, therefore it is equal to 3 units in its length. In the next step we did the construction, that is to say, on this point S, we do perpendicular on the diameter PM. Again, from point S, we do perpendicular on the diameter PM. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and chord PM, and the diameter PM. This point is point N. So by doing this construction, we can do the right triangle ONS. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if you define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other. So in this triangle ONS, this angle equals to alpha, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus alpha. 1 equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this side, upper triangle PQO, this angle equals to alpha, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus alpha according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that the upper right triangle PQO is similar to the lower right triangle ONS. I will explain anyway why those two right triangles are similar to each other. First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the figures of the upper right triangle PQO correspond equal to all the figures of the right lower triangle, triangle ONS, and therefore those two right triangles are similar to each other according to angle similarity rule. So I repeat again, if you found out that the right upper triangle PQO is similar to the right lower triangle, triangle SNO, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SN on the right lower triangle SN of the right lower triangle SNO over side PQ of the upper right triangle PQO is equal to side SO of the lower right triangle OSN over side PO of the upper right triangle PQO. Because again, we derive that side SN of the lower right triangle SNO over side PQ of the upper right triangle PQO is equal to side SO of the right lower triangle SNO over side PO of the upper right triangle PQO. And S is the missing side, so we leave it as it is, over PQ. PQ is X, and it is equal to OS. OS is 2, according to what is given in the question, over PO. PO is the radius of the circle that is free. So in total, we found out that Sn over X equals to 2/3. Here we multiply this equation by X and found out that the missing side Sn equals to 2/3 X. This is the missing side Sn that is equals to 2/3 X. In the next step, we defined the size of this angle as beta. So in the green small right triangle S and M, this angle equals to beta. This angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. This is the sum of the angles in a triangle. Likewise, in the big right triangle PTM, this angle equals to beta, therefore angle beta is the common angle that belongs to both triangles. This angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus beta, according to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that the big right triangle PTM is similar to this small right triangle NSM, according to angle similarity. I will explain anyway why those two right triangles are similar to each other. First of all, this is angle beta, that is a common angle that belongs to both triangles. So we can write out that angle beta equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta, and therefore they are equal to each other. So we found out that all the figures of the big right triangle PTM are corresponding equal to all the figures of this small right triangle NSM. And therefore, those two right triangles are similar to each other according to angle similarity rule. So again, we found out that the big right triangle PTM is similar to the small right triangle MSN according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side Sn of the small green right triangle SNM over side PQ over side PT of the big right triangle PTM is equal to side SM of the small green right triangle SNM over side PM of the big right triangle PTM. But again, from the fact that the big right triangle PTM is similar to the small right green triangle NSM, we will derive that the following relationship exists between their sides. We will derive that side SN of the small green triangle NSM or side PT of the big right triangle PTM is equal to side SM of the small right green triangle NSM over side PM of the big right triangle PTM. We already found out that SN equals to 2/3 X over PT. PT is A according to our definition, and it is equal to MS. MS is the missing side, so we leave this it is. Over PM. PM is the diameter of the circle. The radius is 3, therefore the diameter is 6. Therefore PM equals to 6. So in total we found out that 2/3 X over A equals to SM over 6. Here we can multiply this equation and finally found out that X times 6 equals to ASM. 6 over 3 is 2, and 2 times 2x is 4x. So in total this expression equals to 4x, and it is equals to ASM. So according to equation 1, we found out that ASM equals to 4x. So we can implement rule 15 in our drawing. Repeat quickly on rule 15. According to rule 15, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. So, in the drawing we have a circle, and we have here chord AB that intersects with chord CD at point O. Again, chord AB intersects with chord CD at point O. So in this drawing, the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule 15 in our drawing. Why? Because in our domain we have chord TM that intersects with chord AB at point S. Again, chord TM intersects with chord AB at point S. Point S is the intersection point of chord AB with chord TM. Okay, again, in our domain we have chord TB that intersects with chord AB at point S. So all the requirements of rule 15 are satisfied, and therefore we can implement in our domain rule 15. According to rule 15, TS times SM equals to AS times SB. Again, TS times SM equals to AS times SB. And again, according to rule 15, in our drawing, TS times SM equals to AS times SB. TS is A, SM is the missing side. And TS is A and SM is the missing side, so we leave it as it is. And it is equals to AS. What is the length of AS? AS in total equals to AO plus OS. So AS equals to AO is the radius of the circle that is 3, plus OS that is 2 according to what is given in the question. So in total AS equals to 3 plus 2, that is 5. So AS is 5 times SB. SB is 1 according to what is given in the question. So in total we should find out that A times SM equals to 5 times 1. 5 times 1 is 5. So in total, according to equation 2, we should find out that A times SM equals to 5. This is according to equation 2. And according to equation 1, we already found out that A times SM equals to 4x. So we have two different equations for ASM. Therefore, we created equation 3 that says that ASM according to equation 1 must be equal to ASM according to equation 2. And again, we created equation 3 that says that ASM according to equation 1 must be equal to ASM according to equation 2. ASM according to equation 1 equals to 4x, and it must be equal to ASM according to equation 2. ASM according to equation 2 is 5. So in total, according to equation 3, we should find out that 4x equals to 5. Here we divided this equation 3 by 4, and finally found out that x equals to 5 quarters. Or in terms of numbers, it is 1.25 units. So if you found out that the length of this line segment PQ is equal to x, it is equal to either 5 quarters units, or in terms of numbers, PQ that is equal to x is equal to 1.25 units in its length. Okay, thank you very much.